Well, hi everybody. I'm really happy to be here today at Nodes. This is one of the most fun events that we get to do over the course of the year, and I hope you guys had a really great time in the keynote. On this best practices track, we're going to talk a little bit about graph integration in the cloud. And so, just a tiny little bit about me, because I think that the announcement or my introduction might have gotten muted. My name's David Allen. I'm the global lead cloud architect here at Neo4j. I'm really easy to get a hold of and would love to, talk and interface with folks in the community who find some of this architecture pattern stuff interesting. So let's get right into it. What I'm going to cover in the next 30 minutes, breaks down into a couple of different pieces. We first want to talk about the challenge of why graph integration is important and what about it is different than integrating with any other technology. Next, I want to talk about kind of like a three-step model for how you can think at a 50,000 foot level about how we go about addressing integration problems and issues. And the bulk of my talk today is really about patterns. So I'm going to give examples in this talk of particular technologies that you might integrate with so that I can make it concrete. But I know that those technologies aren't going to be necessarily the ones that you pick inside of your organization. And so we want to think more in terms of patterns or recipes, not that this particular system is the end all be all, but how we would assemble the DNA of a good integrated solution. And at the last section, we're going to talk about what's next. And, being that this is the best practices track, how to think about this and what the best practices are for approaching integration. But let's start off with the challenge. Okay, so obviously, I think that graph is valuable, and you do too, because you're here at Nodes 2021. But it's really important to acknowledge that graph is only one part of a much bigger picture. And so usually this is what I would call the system of systems view. So a lot of people, when they first approach Neo4j, they're like, okay, great, it's a graph database. And so I can put my data in and I can query it out. But so the thing about that is that the database exists as part of some subsystem. And that subsystem may connect to another system. And then inside of your enterprise, you end up having a system of systems where maybe there are 10 different systems that all need to talk to one another. And so there are these different levels of analysis, right? And so when we speak of graph integration, we're not necessarily talking about how to make our driver program work together with the database, but we're thinking about the interchange of data between systems as part of that system of systems. Now, that's a big enough challenge in and of itself. But what we find in our customer base is that these workloads are really moving around quite a lot. A lot of workloads are already in the cloud, and the ones that are not in the cloud are generally making plans to go there, either for cost or efficiency or technology reasons. And we see around us, just because this is the technology business, that everything is changing super quickly. And the cherry on top of all of this is that if you have a successful system, that means that it's going to have a long lifetime, and it also means that it's going to have a long maintenance tail. And so when we think about these best practices for integration, we have to take all of this challenge into account. One of my old colleagues was really fond of this saying, we are all building the legacy systems of tomorrow. And kind of what he meant was that the price of success when you're building an IT system is that it's going to last for years, and it's going to be the legacy at some point. And so we need to think ahead and architect for success, so to speak. So broadly, the way we build these kinds of systems today kind of falls into two models that I often talk about as the solar system model or the Lego block model. And so in the solar system model, you pick a golden hammer or a great tool that does most of the stuff that you want, might even be Neo4j, and you place that as the sun at the center of your solar system, and then all of the technical components of your system tend to revolve around that center. Okay, so if you put all of your data into Neo4j and then everybody has to talk to Neo4j, put stuff in, pull stuff out, that's probably a solar system model. Now, a more modern way of building cloud applications is a little bit more Lego blocky, in the sense that you have this wide variety of different tools and technologies and platforms and APIs and all of those different things. And we don't necessarily place any one single technology in the architecture as primary, but what we do is we snap together Lego blocks, and we reuse these components to build higher level systems. So Part of the challenge then is that as time goes on, as people get into the cloud, you start to see more and more components, and people are using those same components to build more and more different kinds of systems. And so you can start with the Lego blocks on the left, and you can build all sorts of things out of that, whether it's a race car or an art sculpture or an actual building. It's all made of fundamentally the same stuff according to a different architecture pattern or construction plan. Now, to underscore the issue about how quickly this stuff is changing, as an architect, a site that I use a lot is called cloudcompare.in. And so what's really great about this site is that it lists most of the most popular clouds along the top. And then the rows are basically all of the different services that they offer. And so, folks who've used AWS, they're probably familiar with EC2. This is how you get a virtual machine out of AWS. But this site will allow you to sort of crosswalk and see what the equivalent offering is from all of these different clouds. So AWS has EC2, Azure has virtual machines, and Google has a service called Compute Engine. They're all architecturally, in the Lego block sense, all the same Lego block, but they have different names, slightly different technical parameters, slightly different pros and cons. So there are probably like a couple dozen different product categories or types of Legos that are in the box of any of these cloud providers, and the velocity is enormous. So if you're a cloud architect, you may be already subscribing to this newsletter called Last Week in AWS, and it's frankly mind blowing. They have a dozen product announcements per week, and honestly, the smartest architects out there can not really keep up with what's going on. There's so much change happening in this space over time. Okay, so we got lots of Lego blocks. We've got complex ways of snapping them together and building systems. But then there is this migration journey that all of our customers are going through. And so when you get involved with a customer and you watch them develop over a course of, say, 2 or 3 years, you see consistencies in their journey. So the first thing they're usually trying to do is they're trying to get out of their on-prem environment and go to the cloud. And so that usually looks like replacing blade servers in a data somewhere with a virtual machine. And the kind of challenges that they encounter there typically involve identity and access management, networking, and then how to connect systems back to their, what's left of the on-prem system that isn't migrated yet. So in the second phase, they might be trying to modernize, and that involves adopting managed services and doing less work. So here's where they might stop running Neo4j themselves, and they might upgrade to Neo4j Aura as a fully managed service. And that comes with its own set of challenges in terms of operation modernization, making sure that all of the security boxes are checked and so forth. And then finally, a lot of companies that are doing the best these days are really trying to transform the way that they do technology. And that's usually with things like native services integration, where you get full platform benefits. And it tends to draw in issues of culture and development approaches within these organizations. So again, as we go through this, I want you to keep in mind that successful systems have long lifetimes, long legacy tails, and whether they know it or not from day one, they tend to be on this kind of journey that we're talking about right now. So let's get to graph data integration, or graph integration specifically. Three-step model. This is pretty much as high level as you can get. This is truly a 50,000-foot view of a graph system. Well, Neo4j is a database, and so you can think of it like a can. You put data in and you take data out. It's really that simple. So the 3 steps then are, in any kind of an architecture that's using Neo4j, typically you're doing 3 things. There is data ingress. That is, you got to get stuff in, because there's no graph value if you don't have a graph in the middle. In the middle, there's a graph value add. You might be doing this in any number of different ways. It might be a long path query. It might be a recommendation system. It might be identifying potential fraud, or it might be doing something really advanced with GDS. No matter what it is, when you get that data into the center, you're adding value to some business process or to the data itself using graph. And then finally, the third step is data egress. In order for that value to actually mean anything or go anywhere in the world, there's got to be some next step to it. Sometimes the data goes straight into the eyeballs of a business analyst who's looking at it and who makes a business decision on the basis of whatever came out of graph. And sometimes it's going to some downstream system, whether that's a data warehouse or an ML system, whatever it might be. Now, on this slide, we've got a set of questions that go along with each of these three steps. Okay, so for ingress and egress, these are kind of mirrors of each other. In both cases, it's just data movement. And we want to ask questions like, well, how much data do we need to move? How often do we need to move it? Where is it coming from in the case of ingress? Is it coming from a data warehouse, a flat file? And then the modality of that data movement. And so this is where you get into push versus pull. So is some upstream system going to throw data over the fence to Neo4j, or does Neo4j need to pull it through some other architecture? And so you start to need to think about these kinds of questions in order to pick any kind of an integration approach. And that's why we like to frame it in this way, in this three-step way. So let's talk about a couple of patterns and what we might call reference architectures for describing how these pieces fit together. Now, this is a big one, and it involves a lot of Google-centric technologies. But as we go through this, and when you see the recipes later, you'll see that the Google-specific technologies aren't what's important here. It's the class of technology that's important. So a lot of companies are going to be starting with a set of files or a set of existing business applications on the far left. And they're going to tend to design an ingest and a process layer for getting data on the ingress side into Neo4j. Now, that ingress can further be kind of subdivided into batch versus streaming ingress. And so at the ingest layer, you're going to see typically technologies like message queues, data warehouses, Kafka, bulk storage, and Spark. At the processing layer, you're going to typically see things like cloud functions. There might be more Spark at that layer, or there could be third-party ETL tools like Apache Hop, Informatica, things of those sorts. So, but what we're really doing with those layers is we're taking data from far on the left, ingesting, processing it, and putting it into Neo4j. Notice how I'm separating ingest and process here. We're going to talk more about that in a minute. So the data gets into the Neo4j can, so to speak, and then they're going to bring any number of graph analytic techniques to bear on those graphs. And so I usually think of these as falling into three broad categories. You've got graph visualization. That helps you identify a hypothesis about what might be going on in your data. You've got graph queries. These are just vanilla Cypher queries that you use to extract data out of a graph. And then you have graph algorithms, and that's where stuff like graph data science, GDS, and so on comes in. Irrespective of how you do your analysis, there tends to be this downstream layer. So you've got a presentation layer where folks very commonly use some of the classic BI tools. This is where your bar charts, pie charts, stacked bar charts and all of that kind of stuff comes in, or where you may even be using Neo4j Bloom to visualize the shape of the graph. And in some of the most fun customer engagements that I get involved in, there's typically some kind of a machine learning layer downstream of that as well, where maybe we're taking the results of some GDS computation and then pushing it downstream to something like AutoML, Data platforms like that. A lot of times they're going to be using very similar technologies from the ingest and the process layer to do that data egress on the other end. So let's get more specific with another example. So this comes from a case I was working on recently where a customer was doing some patient analytics. They were using healthcare data and they wanted to know about patient outcomes. So they had a very large number of documents that they would upload into a cloud storage bucket. On Amazon, this could be S3 or Azure Blob Storage. Again, the specific technologies don't matter here. We need to think about it in terms of like Lego blocks. This was a bulk storage technology for documents. So when a document would get uploaded, that could then trigger a piece of code that would use an API to annotate or extract metadata out of those documents. So every cloud has some variant of an API that you can use to do OCR, for example, or that you can use to do entity resolution and draw out from text mentions of names, locations, and times, and so forth. So that metadata can then be put onto a message queue, in this case, Cloud Pub Sub, and that can trigger a cloud function. So the cloud function is a little bit of code that can write the data to both BigQuery and to Neo4j at the same time. And so if you look at the top line of this slide, what we've done is designed a streaming ingest architecture that can go from any set of PDFs and documents all the way through into the knowledge graph in Neo4j in the center. So look at that entire top row and think to yourself, well, in that three-step model we were describing earlier, that entire top row is ingest. So in the knowledge graph in the center, we might use GDS to do some graph feature engineering, and we might add value to that data by doing community detection or by doing a centrality measure on particular patients in our database, and then by simply adding those back as properties to the graph. That is the graph value add step of the three-step model we discussed earlier. And the egress or exploitation phase downstream, you might use the Neo4j connector for Apache Spark and pull data from both BigQuery and Neo4j at the same time, kind of mix and match those different data sources, and then feed it into your downstream ML as a service platform or whatever other technology you might be using, including other data warehouses and so forth. So when we think about these inputs and outputs, we've already touched on some of these critical considerations. And so these are stated as rhetorical questions because when you leave this session and when you go in and doing this in your organization, I can't provide you answers to these questions. These are the questions that you need to ask when you're trying to put this together for yourself. So a lot of customers, they want to know whether they should do batch versus stream. And they usually start off with batch just because it's easier. And as an architect, I typically try not to answer the question of whether batch or stream is better, but I instead try to chop it down into some sub-questions that help lead us to the answer. So for example, what are the timeliness requirements of the data? How fresh do you need your data? Okay, if your data needs to be less than 5 minutes old, you probably want a streaming ingest pipeline. And if you're okay with nightly updates, then probably batch is an easier way to go. So the second characteristic is, volume. How much of it is there? So typically, the higher your performance needs and the higher the volume that's involved, the more you're going to want to go the batch route. And the third is consumer pull versus producer push. So where the streaming architectures do really, really well is when the producer is pushing data to Neo4j, whereas batch does really well when Neo4j needs to pull it as a consumer from an upstream system. Like let's say your data warehouse does an update on a weekly basis, and then Neo4j needs to pull whatever changes. That's probably more of a batch operation. The second one that nobody ever thinks about, but it always ends up biting them, is how clean the data is. Okay, so when we think about these, whether it's streaming or batch architecture, there's that old saying, garbage in, garbage out. Okay, the principle when we're doing this kind of data engineering work is that you need to clean up the data as early in the process as possible and as soon as practical. And the longer in your pipeline you wait to clean up the data, typically the harder it is going to be to do that when you get to it. So before you begin these kinds of integration processes, one needs to have an understanding of where the data is coming from and what its quality challenges are so that they can be fixed upstream. A major anti-pattern is to just go ahead and slam it all into the graph and then later discover the data quality problem and then fix it within Neo4j. The reason that's an anti-pattern is because you're typically going to have an integration that's going to be continually shipping you data, which means that you're going to be continually cleaning it up inside of Neo4j. It always pays to clean it up as early in the process as you can. The third consideration is what your graph data model is. So when we do graph data integration, a thing that slips people's minds sometimes is that since the data is usually coming from a non-graph technology, let's just say it's a data warehouse or Postgres, something like that, all right? Implicitly, whenever we move this data, we're doing a formalism transform, where we're changing the data from tables into graph, or we're changing it from JSON documents, for example, into graph. That then implies, if we're changing formalism, that you have basically an as-is data model, and then you have a to-be data model, which is maybe your graph data model, and then there's some set of mappings between those two things that describe how does this table turn into that graph and so forth. And so when you go to do this kind of integration work, you very rapidly find This is not an answerable question without knowing what your target graph data model is and without knowing what your source model is. So basically, what we've got here is three separate considerations. There's the data moving. There's whether or not the data is any good. Are we doing garbage in, garbage out, or is the data clean? And then the third is when it's moving, it's transforming. How is that happening? Let's take a moment and talk about a formula for batch data movement. Again, this is the case usually where the consumer wants to pull data through from another system. And so I'm going to explain this, but the basic recipe is source system plus batch pull plus transform plus write. And so what I mean by that is that the source system could really be anything under the sun. It can be Snowflake, Postgres, MongoDB, files in an S3 bucket, doesn't even really matter. The batch pull is going to be a query or an extract step. And so what that batch pull is going to look like is going to depending on the source system. So if you're coming from Postgres, the batch pull could be nothing more than select star from table. And if it's S3, it might be like loading a JSON file off of S3. So the next step is to transform. And then basically what we're doing is mapping whatever the source structure was onto that target graph structure. And then we're finally writing it to the target system, which is usually Neo4j. So there's going to be, for example, a bolt driver in the mix and some Cypher queries that get executed to write the transformed data into a graph shape. Now, when you're doing batch data movement, sorry, the tech options are usually variants of the things that you see on this cloud. So on this slide, like we see a lot of Spark, we see a lot of Databricks, EMR, Dataproc, things like that. We see a lot of cloud managed tools that do things like bulk data movement, whether it's Apache Beam, Cloud Dataflow, AWS Data Pipeline, and then traditional ETL suites like we mentioned before. So if you call my reference earlier to that cloudcompare.in site, and you're saying, well, David, I don't get what you're talking about. What is that in my cloud or in my environment? I would say go to Cloud Compare and look up the big data managed cluster as a service offerings and look up the cloud ETL offerings. And we're talking about, technologies in that category are what people are generally using for batch data movement. So for streaming data movement, this is typically event driven, and it's usually when the producer of the information is pushing the information to you. The recipe here is you've got a source system, you're going to pair it with an adapter, you're going to pair that adapter with a queuing system, and then a trigger consumer. So let's break that apart. So the source system, again, it can be literally anything under the sun. It can be any database, including Neo4j. So the adapter is going to be something like a Debezium plugin for a database, or if you're familiar with the Neo4j adapter for the Neo4j connector for Apache Kafka, Neo4j streams, things along those lines, you can set it up so that whenever a transaction commits into Neo4j, it fires a message out on a Kafka topic, for example. And so that is the producer pushing the data out to somebody else in the architecture. Now, the queuing system, again, there's a lot of these. I've only listed 4. These are the 4 that we most often come into contact with, but they are by far not the only ones. You got Kinesis, PubSub, Confluent Cloud, which is a form of Kafka. You've got Azure Service Bus, and another one that I forgot to list is Amazon MSK, or Managed Streaming for Kafka. Finally, the last piece is a trigger consumer. Now, remember, we've said that in a streaming architecture, the producer pushes the information. So when a message arrives on the queue, you need a trigger consumer that acts on the basis of that message. And so typically, that bit of code is going to be a containerized custom application or a cloud function like an AWS Lambda. And in that earlier architecture, I had a Google Cloud function that was taking something off of PubSub and that was writing it into Neo4j. Now, again, if you want to crosswalk this for your technology needs, check out Cloud Compare and go to these categories of offerings. Look for queuing services and microservice app development platforms. That's what, when I say queuing system, they're saying queuing services. And when I say trigger consumer, that's where microservices app development kind of comes in. The key thing in all of this to future-proof this is to separate concerns. Again, we got three key questions, and we really, really want to try to keep them separated. One is, how did the data get out of the source? The second is, how did it get cleaned up and transformed? And then the third is how it actually moved across the wire and what protocol you used and so forth. The reason it's so important to keep these concerns separate is so that you can independently evolve each. Remember, the penalty for a successful system is that you get to maintain it for years. And so these systems have long lives and maintenance tails. And so by separating concerns up front in the way that we architect them, we kind of give ourselves some flexibility to adapt them later on in the process. On the right, I've got this little meme about what I would say is the typical anti-pattern that I run into. So basically, early on in the learning process, somebody writes a Python script that loads some JSON data and puts it into Neo4j. That's great. It's beautiful. It gets the job done. However, when you use a Python program to do all of your data loading, typically what you're doing is you're piling all three of those concerns into one monolithic Python program. When you then go to scale, you find yourself painted into a corner. So we've got just a few minutes left. Let's wrap it up with best practices. This is the best practices track, and the only way that I know how to do that is with memes. Okay, so I think of best practices as having like a light side and a dark side. And so I wanted to also give you a couple of worst practices. Okay, so let's start with the worst practices. Put everything into one script. If you put everything into one script, you will be combining concerns. And what that is a recipe for is having a really, really huge, complicated, poorly running script that only one person in your enterprise knows how it operates. The next anti-pattern might be dump everything into CSV. Forget an integration pipeline, but rather export your data warehouse into CSV and then use load CSV for all data import. This will guarantee that you get to do things pretty manually every time, and that if anything in your source table format changes, that your load CSV process breaks when you go to re-import it the second time. The third is kind of a variant of this. Like if you mix data quality cleanup work and graph transforms in one place, that's going to cause you maintenance problems later on. And so where I most see this in our customer base is people come with like 80-line Cypher queries where you can really tell that they're taking a really complex data source, transforming it into Cypher, and also trying to like remove null values and translate codes and do all sorts of things inside of one huge Cypher query. Another anti-pattern is to implement all steps as custom VMs. This will litter infrastructure all over the place that you're going to have to maintain later on. Another anti-approach is to pick an approach before you know your timeliness and quantity needs. And this is just a variant on the old advice: know your requirements before you begin. I find that sometimes people get attached to particular tools and approaches, and they might say, Apache Spark is the answer. What was the question again? And so when you pick that approach before you know your requirements, you're almost certain to end up with a poor fit for your requirements. And the last anti-pattern is to get attached to your Legos. And what I mean by that is when we're designing these architectures, we're going to be mixing and matching lots of different technologies fundamentally. And we want to be able to swap them out independently. There isn't any one tool that's the end-all be-all. And as an architect, sometimes we're looking at the different queuing systems as being relatively substitutable for one another, in that they both architecturally, or they all architecturally do the same thing. And so I find that it doesn't pay to get attached to your Lego blocks, because it makes it harder to swap them out later on. And if your system is going to live for 5+ years, sooner or later, you're going to need to swap out one of those Lego blocks. So what are the best practices now? I've told you about all the horror stories. How can we do this right? Well, first is to have a big picture. Know what your current architecture is and know what your to-be architecture is. And it's okay to have an aspirational architecture that's going to take you a year to get to. You should be able to describe for your system what the 3 steps are: ingress, value add, and exploitation. And even better, if you can draw a single PowerPoint slide of that, it's really going to help you in the long run. Next best practice is to separate cleaning from transformation and clean as early as possible in the pipeline, like we covered. Where possible, use cloud services to offload maintenance. And if you remember that transformation journey, in the transformation step, we're using a lot more of these cloud managed services precisely because they allow us to focus on the logic of our app and not on the maintenance, care, and feeding of a lot of different software systems. So it allows you to focus. And for the last two, first is establish some integration SLAs, and those are things like how much timeliness, quantity, and quality that you need out of your data, what's acceptable. This prevents gold plating your solution, and it also tells you whether or not you've hit the mark and whether or not you've succeeded. And then finally, know what those Legos do for you. So understand the meta Lego block level so that you can swap them out later as needed. Maybe your company is going to need to go through a technology upgrade for whatever reason. Maybe it's going to be a security issue. Maybe it's going to be a better deal that you can get on a component down the line. But you want to be able to swap those out. And I want to thank you for taking the time. And please do, if you've tuned in, make sure to stick around for the panel discussion for this track.